What specific problem does your proposed mutation testing methodology aim to solve in the context of missed code size optimizations for compilers?
Our proposed mutation testing methodology specifically aims to identify missed code size optimization opportunities in compilers, which is critical for applications in embedded computing, mobile applications, and firmware software. Traditional methods of compiler testing, such as random program generation, are often complex and require extensive maintenance, making them less effective for new programming languages. By utilizing large language models, LLMs, to iteratively mutate a simple seed code, we simplify the process of generating test cases while targeting optimizations that may have been overlooked. Our approach includes 4 differential testing strategies that compare the output of compilers under different conditions, allowing us to detect regressions and inconsistencies in code size optimizations. Ultimately, we successfully identified 24 bugs in production compilers across C, C++, Rust, and Swift, demonstrating the effectiveness of our methodology in addressing this specific problem.
How does the proposed mutation testing methodology work? Illustrate the process step by step, from seed code to identifying suspicious compiler behavior.
The proposed mutation testing methodology begins with a simple seed code, which is iteratively mutated using a large language model, LLM. First, a prompt is constructed that instructs the LLM to apply a randomly selected mutation from a predetermined list of mutation instructions, such as adding control flow or modifying existing conditionals. After each mutation, the modified code is compiled, and a series of differential testing strategies are employed to identify any suspicious compiler behavior. These strategies include dead code differential testing, where the addition of dead code should not change the program's semantics, and optimization pipeline differential testing, which compares code generated under different optimization settings. If a violation is detected, indicating that the compiler failed to optimize correctly, the suspicious compilation results are reported to the user for further investigation.
Can you provide a simple yet illustrative example that demonstrates how the LLM mutates seed code and how differential testing is applied subsequently?
In our methodology, we start with a simple seed code, such as a trivial function that evaluates a constant. The LLM is instructed to mutate this code by randomly sampling from a predetermined list of mutation instructions, which may include adding control flow statements or modifying existing conditionals. For instance, if the seed code is a simple loop that checks if a variable equals 10, the LLM might mutate it to check if the variable is greater than or equal to 10 and less than or equal to 10, thereby increasing its complexity. After each mutation, we compile the modified code and apply differential testing strategies, such as dead code differential testing, which checks if the addition of dead code changes the program's semantics. If the compiler fails to recognize the added dead code and produces different output, it indicates a potential missed optimization opportunity, prompting further investigation into the compiler's behavior.
What are the theoretical or practical advantages of your mutation-based approach over traditional random program generators like CSmith, particularly in terms of human effort and maintainability?
The mutation-based approach we developed offers significant theoretical and practical advantages over traditional random program generators like CSmith, particularly in terms of human effort and maintainability. Firstly, our method requires only a simple seed program and utilizes an off-the-shelf large language model, LLM, to iteratively mutate this code, drastically reducing the complexity and length of the codebase needed for test case generation. Our implementation is under 150 lines compared to CSmith's over 40,000 lines. This simplification minimizes the human effort required for training and maintaining the generator, as it does not necessitate the extensive language-specific expertise required for grammar-based generators. Additionally, our approach allows for easier adaptation to new programming languages by simply changing the prompt and compiler invocation, making it more maintainable as languages evolve. In contrast, traditional generators like C-Smith often become outdated and require significant updates to accommodate new language features, which can be prohibitively expensive. Overall, our mutation-based methodology streamlines the process of generating compiler test cases while maintaining effectiveness in identifying missed optimization opportunities.
How did you validate the effectiveness of your method in identifying missed optimization opportunities? What metrics or benchmarks were used in your experiments?
To validate the effectiveness of our method in identifying missed optimization opportunities, we employed 4 differential testing strategies: dead code differential testing, optimization pipeline differential testing, single compiler differential testing, and multi-compiler differential testing. We ran each strategy for 8 hours using the Llama 3.1 model, evaluating the total number of completed tests, the number of compilable programs, and the number of violations that indicated suspicious compiler behavior. The experiments revealed that the larger 405B parameter model was more effective in finding bugs, as evidenced by a higher violation rate, while the smaller 70B model produced a greater total number of violations due to its faster inference time. In total, we discovered and reported 24 bugs across C, C++, Rust, and Swift compilers, demonstrating the method's capability to identify missed optimizations effectively. The metrics used included the total number of programs tested, the percentage of compilable code, and the count of violations triggered during the testing sessions.
What are the major limitations or potential drawbacks of your method, particularly regarding the use of LLMs for code generation, and how might these affect the results?
The major limitations of our method stem from the inherent challenges of using large language models, LLMs, for code generation. Firstly, LLMs can produce syntactic and semantic errors, which complicates the identification of true compiler bugs versus mistakes made by the model itself. This necessitates the use of heuristics and analyses to mitigate false positives, but it does not eliminate the risk entirely. Additionally, the LLM may misinterpret instructions, such as confusing dead code with code that does nothing, leading to invalid test cases that could skew results. Lastly, while our approach allows for a simpler code generation process compared to traditional grammar-based methods, it sacrifices the guarantee of correctness, which could result in the generation of non-compilable or incorrect code that may not effectively test the compiler's optimization capabilities.